We are going to continue with the topic of maximizing or minimizing multivariable functions, and today we're going to talk about a technique called Lagrange multipliers. So this is best illustrated by starting with an example. So the production of widgets in millions depends on compounds x and y by a function f of xy equals x to the 2/3, y to the 1/3. And this is a Douglas-Cobb production function. And this is the function that we want to maximize. But we're given additional information that 1 ton of compound X or Y costs $1 million, and that the total budget for producing widgets is $3.78 million. So we don't want to go over our budget of $3.78 million. We want to spend that entire budget. So we need a function that represents the total amount that we're spending on compounds X and Y. So that function is going to be g of xy, and that function should be the cost per compound ton of compound X times the amount of compound X. So it costs $1 million per ton times X tons of compound X plus $1 million per ton times Y tons of compound Y. And so the function X plus Y represents the total cost of the two compounds. We want that function to be set equal to $3.78 million so that we spend all of our budget, but that we don't go over our budget of $3.78 million. And we call this function a constraint because we know that our total cost is going to be X and Y, but we're constraining how much we can spend by the budget that we've been given of $3.78 million. So if you look at the graph on the left, our goal is to maximize the function f of xy, which is represented by those red to yellow level curves. But we're constrained by the fact that we have to stick to the budget line, g of xy equals 3.78, which is the blue line that you see. So we're only allowed to choose x and y values that are on that blue line. So for example, if we choose a small x and a large y, you can see that we're on that red level curve, and the production level will be 0.5 million widgets. But if we choose, say, a larger x and a smaller y, then we can produce 1.5 million widgets along that orange level curve. So now we can look at the graph and see if there's a point along the blue line that maximizes our production level. And by inspecting, we can see that a point right about here, say where x is 2.5 and y is 1.5, that point will give us a production level of 2 million widgets. So from the graph, we can see the maximum occurs when f of $2.5 million for compound X and 2.5 tons of compound X and 1.5 tons of compound Y equals 2 million widgets. Now, what was special about that point? Well, hopefully you notice that the constraint, g of xy, looks to be tangent to that level curve where f of xy is equal to 2 million widgets. And so when the constraint is tangent to that curve, f of x, that level curve for f of xy, that's where we're going to get our maximum. Now, we need to figure out some sort of condition for which that constraint is going to be tangent to the level curve of f. And the way we do that is we have to use a little bit of theory from multivariable calculus, and so I'm going to try to fill in some of the details. So something that you should be aware of is that when you take the derivative of f with respect to x and the derivative of f with respect to y, you can form a vector with those derivatives. So I can make a vector that points in that direction, and this would be the derivative of f with respect to x and the derivative of f with respect to y. And that vector will always be tangent to level curves. So if I picked a different point at a level curve, that derivative vector would be tangent to that curve. Okay, so I could pick a bunch of these. I could pick one like that, or I could pick, say, one like that. And the derivative vector is always going to be perpendicular to those level curves. Well, the same thing is also going to be true for g of x. So if I pick points along g of x, the derivative is always going to be perpendicular to g of x. But there seems to be one point where those two derivatives align. And that's the point right there, which is about 2.5, 1.5. So you'll see the two derivatives are pointing in the same direction. One of them could be longer than the other if we like. So we could say one of them is that long while the other one is that long. But the two derivatives will point in the same direction so that one derivative is a multiple of the other. And this is where we come up with the concept of Lagrange multipliers. Okay, so in order for those two derivatives to line up, we need both the x and the y derivatives of f to be multiples of the x and y derivatives of g. So looking at this theorem, so we suppose that the function f of xy has a maximum or minimum at a particular point. We'll call that point x0, y0, subject to the constraint that g of xy has to equal a constant. Then for some constant lambda, our partial derivative of f with respect to x at that point needs to be a multiple of the partial derivative of g with respect to x at that point. And the partial derivative of f with respect to y needs to be a multiple, a constant times the partial derivative of g with respect to y at that point. So if we can find a point where the partial derivative of f is with respect to x is a multiple of the partial derivative of g with respect to x, and the partial derivative of f with respect to y is a multiple of partial derivative of g with respect to y, then that's where a maximum or minimum of the function will occur. And the constant lambda, so this is the Greek letter lambda, is called the Lagrange multiplier. So L for lambda, L for Lagrange. Okay, so now let's use this idea to come up with the values of x and y that will maximize production. Okay, so we want to maximize the function f of xy equals x to the 2/3, y to the 1/3. And our constraint is g of xy equals x plus y, 3.78. So in order to begin, we'll need to find df dx. df dx in this case is 2/3 x to the minus 1/3 and times y to the 1/3. and df dy is 1/3 times x to the 2/3 times y to the minus 2/3. We'll also need to find the derivative of g with respect to x, which happens to be 1, and the derivative of g with respect to y, which also happens to be 1. And so if the derivative of f with respect to x is supposed to be a multiple of the derivative of g with respect to x, then we should have that 2/3 x to the minus 1/3 times y to the 1/3 should equal lambda. And 1/3 x to the 2/3 y to the minus 2/3 should also equal lambda, and both these lambdas are times 1 for the derivatives of g with respect to x and y. And so this gives us two equations for x and y. So I'm going to label them equations 1 and equations 2. So at this point we have two equations. The equations have the variables x, y, and lambda. And so I have two equations and three unknowns. And so I won't be able to solve these equations unless I come up with some sort of third equation. And so the third equation is going to be our constraint, because that constraint also relates x and y. Now, if we want to proceed to solve this problem, I'm going to set equation 1 equal to equation 2, because both of them are equal to lambda. When I do that, I get that 2/3 x to the minus 1/3 y to the 1/3 equals 1/3 x to the 2/3 y to the minus 1/3. And so hopefully you can immediately see that I can multiply both sides by 3 to get rid of the 3's in the denominators on both sides. Okay, so then I'm going to multiply both sides of the equation by x to the 1/3 That's to get rid of the x to the minus 1/3 on the left. And then I can see that I've made a small mistake, that this is y to the minus 2/3. I'm also going to want to multiply both sides by y to the 2/3. And that's to get rid of the y to the minus 2/3 on the right. So if I do that, what I have left on the left is just 2y. And what I have left on the right is just x. So that x equals 2y. Now that I have that relationship, I can substitute that into equation 3. So that x plus y equals 3.78 means that really 2y plus y equals 3.78. And that tells me that 3y equals 3.78. So y equals 1.26. Once I have that, then I know that x is equal to 2y, so x is equal to 2.52 million tons, because that is twice y. And so y equals 1.26 million tons. And that tells me that f of 2.52 million tons and 1.26 million tons. Now I'm going to substitute that into this equation, 2.52 to the 2/3, 1.26 to the 1/3, and that's going to give me a total of 2 million tons. And that mostly matches the answer that we had gotten when we looked at the graph. We had guessed that the answer was somewhere around 2.5 and 1.5. It turned out that the answer was 2.52 and 1.26. So that's not a bad estimate that we had done with our previous work on the graph. So that's our first example of how to deal with Lagrange multipliers.